Probability is one of the hardest things that students find difficult in VCE methods, but luckily I would say I'm a bit of a connoisseur when it comes to understanding probability. So let's get understanding and let's try and start with a fresh slate, I know a lot of people don't really like probability. It's a lot of words, it's a lot of interpretation from big paragraphs and whatnot, but let's try and break it down into, parts that we can really understand. So we're going to start off with a really basic example. It's one of the more basic examples that we have in probability, and it's because each of our outcomes are equal probability. So for example, we have rolling a dice here, right? A 6-sided dice. Now, there's 6 possible outcomes, and each of them have an equally likely probability. So each of these outcomes are going to have a 1/6 probability, and that's just because it's 1 for one outcome divided by 6 possible outcomes in total. So each of these are 1/6. Now, obviously, not all events that happen are equal probability. Some examples of things that are equal probability are rolling a dice and also flipping a coin. We know heads and tails are 1/2 each. But obviously, if you have the probability of, let's say, 2 teams playing a sports match and one team is more likely to beat the other, then that probability would obviously be higher, and you can't kind of just split it up equally like we've done here. So it just depends on the event that we're actually talking about and the situation that we're talking about. In this case, it's very easy, and it's kind of implied when you do roll a dice. So when you have anything like a fair event, so a fair event means equally likely outcomes, it's really easy to calculate the probabilities of them. It's just the outcome that you're talking about, or the number of outcomes you're talking about, divided by the total possible number of outcomes. And we have a few examples here to illustrate that fact, and obviously there's different combinations of them. For example, the probability of rolling a 5 is simply 1/6 because it's one possible outcome out of 6 possible outcomes. Probability of rolling an odd number, how many odd numbers are there? There's 1, there's 3, there's 5. So that's 3 outcomes out of 6 possible outcomes. So we have 3 on 6, which is equal to 1/2. Now, you might not recognize this from last year, or you might recognize it. The term for it is conditional probability. Now, conditional probability is that's one of the things that's recycled from year 11 that's kind of skimmed over in year 12. So we're just going to make sure that we understand it now. So how we read this is the probability of rolling a 5 given that the number that we roll is odd. So let's try and break that down. Probability of rolling a 5 given that the number that we roll is odd. So essentially what it's saying is we know that the number that's rolled is odd. What's the probability of that number being a 5? And when you think of it like that, and when you break it down like that, you might see that the sample space, or the total number of possible outcomes, has actually reduced. And that's because 2 is not an option, 4 is not an option, and 6 is not an option anymore. So how many options do we actually have? We have 1, 2, 3. Now, out of those 3 possible outcomes, 5 is obviously only one of them. So the probability of this happening is actually 1/3. Now, this is kind of the conceptual way of answering this question, but there's actually a formula to solve this question as well if you don't really want to do the conceptual way, but I just wanted to tell you guys as a conceptual way so you guys have an understanding of where the formula actually comes from. But before I go through the formula, I just want you to understand that whenever you have a conditional probability, it's always the first event given that the second event actually happens, okay? So when you know that the second event happens, what actually is occurring is you have a reduced sample space. Okay, I'm just going to write that down. Reduced sample space. Now, what exactly is a reduced sample space? It's what I did here, where I took out the 2, the 4, and the 6, because since my number is odd, that reduces them outside of the sample space. The original sample space was all 6 numbers. Now the sample space is only 1, 3, and 5. So when I say reduced sample space, it just means that because the number is odd, it reduces the total possible outcomes that we have in the situation. Now, the formula for this, if we wanted to apply it, is the probability of the intersection between the 2 outcomes that we're talking about here, divided by what's given, okay? So what's the probability of a number being 5 and odd? Obviously, that's just 1/6, because, you can see 5 is a subset of odd numbers, a subset meaning it's just contained inside the other set. So for example, the set of odd numbers is just 1, 3, and 5. The set of 5 is obviously just 5 by itself. So the probability of 5 and odd is the same as just talking about the probability of a number being 5. Now the probability of number being odd, we already talked about before, is 1/2. So I'm doing 1/6 divided by 1/2. That's the same as 1/6 multiplied by 2 over 1, doing state change flip. And you can see 2 over 6 becomes 1/3. So I've got the same answer before, just thinking about it conceptually, but this is just the formulaic way of solving the same question. Now let's practice our discrete probability skills with a complex multi-step probability problem. In this case, we have a drawer. We have a top drawer and a bottom drawer and different ratios of colored socks in each drawer. So in the top drawer, we have 3 out of 4 socks being black, and in the bottom drawer, we have 1 out of 5 socks being black. So we can just assume that in the top drawer, there's 4 socks in total, and there's 3 of them that are black. In the bottom drawer, there's 5 socks in total, and 1 of them is black. Now, let's say we're in the dark and we're trying to choose a sock and match a pair, right? So we have a half probability of randomly choosing the top or the bottom drawer because, the question says there's 50-50 probability, but it just makes sense, right? If you're in the dark, you can't really see what you're doing, so you just choose one randomly. So we can just say the probability of the top drawer, of choosing the top drawer randomly, is 1/2. Now, the next question asks for the probability that a black sock is from the top drawer, or the probability of choosing a black sock from the top drawer. So we can think of this as like a multi-step event, and we use our intersection because we want the probability of choosing the top drawer and then a black sock from that top drawer. So what you do is, okay, what's the probability of choosing the top drawer? It's just 1/2. Now that we've chosen the top drawer of 1/2, there's a 3/4 probability of choosing a black sock. So what we do is we do 1/2 multiplied by 3/4. Now if you want to do the full working out for this question or show even more working out, to be honest, it's unnecessary. But if you want to understand where this comes from, it's because choosing this and these individual probabilities are independent events. So what we'll do is we say black sock, the probability of black sock intersected with top drawer, okay? But obviously you just have to take into account that this black sock probability changes depending on which drawer you choose. So it's 1/2 multiplied by 3/4, which just becomes 3/8. I'll just write that a bit bigger. Cool. Now, what's the probability of choosing a black sock in general? So this is a bit more broad because it's not focusing on the top drawer. It's kind of implying that you can choose a black sock from either the top or the bottom drawer. Now what we should do is think about the different combinations of choosing black socks. So we can either choose a black sock from the top drawer or a black sock from the bottom drawer. Now, a lot of people would draw a tree diagram for this event, which is more than okay in this case. So we can have the top drawer or we can have the bottom drawer, and we can have black or not black, BL for not black, BL dash for not black, sorry. So BL and then BL dashed, okay? So the probability of choosing a top or bottom is 1/2. Probability of black sock there is 3/4, therefore this one is 1/4, this one is 1/5, therefore this one is 4/5. Now if you want the probability of choosing a black sock, it's either going to be down this path or this path, because that's top drawer, black sock, bottom drawer, black sock. So therefore, if we just multiply the probabilities in each branch and add them together, we get 1/2 multiplied by 3/4, which is actually what we did before. I'll just write the full calculation out. And then plus 1/2 multiplied by 1/5. So we get 3/8 added with 1/10. These numbers aren't the best. What's the common denominator of 10 and 8? It's 40. So this becomes, so that was a bit of a thinker. That took me a little while than expected. So this will become 40 by multiplying by 5. Therefore, this one is 15. This one becomes 4. This one becomes 40. Therefore, we get 19 over 40. And that can't be simplified any further. Sweet. Now the last question, which is the hardest part, what's the probability of the sock coming from the top drawer considering it is a black sock? So we can go ahead and use the formula, and then we'll do the conceptual way, kind of backwards to the previous video if you watched it when I introduced conditional probability. So what we can do is we'll say the probability of a sock being from the top drawer and black divided by the probability that it's a black sock in the first place. So the probability of a sock being from the top drawer and a black sock is what we calculated before, which is 3/8. And then we divide it by the probability of it being a black sock in general, which is 19 on 40. So what we can do is go ahead and simplify this fraction using state change flip. So go 3/8 multiplied with 40 over 19. Now a lot of the times when you get to this scenario, a lot of people just multiply across, but don't do that because the numbers get really large. Look for common factors that you can actually cancel out. So this cancels out to 1, this cancels out to 5, and this actually ends up being pretty easy, ends up being 15 over 19. Now, whenever we get answers in probability, it's good to kind of think about if they actually make sense or not, because probability should always reflect real world statistics, let's say, if the numbers are realistic. And in this case, what we can do is think about if 15 on 19 actually makes sense as an answer. Now, how do we actually figure out if it makes sense or not? What we do is we think about what this conditional probability is actually saying. So again, we're going to kind of interpret what the conditional probability means. What's the probability that a sock comes from the top drawer, given that we already know that it's a black sock? So in this case, where can you see a more likely black sock being chosen from? Is it going to be from the top drawer or the bottom drawer? You can clearly see that it's going to be from the top drawer because it just has a much higher ratio and a much higher probability of a sock being black from that drawer. So therefore, if a sock is black, it is very likely to be from the top drawer. That just makes sense, conceptually. So therefore, we actually expect a high probability here, and which is what we get. We get 15 on 19, which is roughly 75% or so. Not quite, but it's around 75%. You can see it's much higher than 50%, which was the original probability of choosing a top drawer. So given that the sock is black, that actually increases the probability of us knowing that the sock's from the top drawer, which, yeah, again, it makes sense conceptually. So it's good in general, not specifically for this question, but just in general to think about if your answers make sense from a probability and a statistics standpoint, because if they do, then your answer is most likely right, and you can kind of ensure, and you kind of, be assured of the fact that you actually did the question correctly. Here's the first new topic for discrete probability, and it's actually probability distributions. A probability distribution is essentially just probabilities summarized in a table, and we're going to illustrate that with this example here. The amount of goals scored by Liverpool in a match. I'm a Liverpool fan. Obviously you can see the number of goals is not that high, right? Because Liverpool, not so good last season. The amount of goals scored by Liverpool in a match is described in the probability distribution below. So we'll have an interpretation, or we'll do an interpretation of this table and what the numbers actually mean, and try and understand how good Liverpool is. And obviously I said they're not that good, but hopefully they do improve this season. Anyway, I'm just going into flashbacks of the depression from last season. So we can see we have a top row here and a bottom row here defined by those leading variables. Now I'm just going to switch sides here. This variable here, x, lowercase x, that represents the possible numbers for the number of goals. In this case, we have capital X goals is just like the general variable describing the number of goals. The lowercase x is describing the specific cases, or the specific, just the different possible values for the number of goals. But x in general, capital X, just represents the number of goals. So this is the possible values for x, capital X. And we denote the possible values of capital X as lowercase x. So, for example, if I wanted, you can see here the probability on the next line is probability of capital X equaling lowercase x. So the lowercase x is the possible numbers. So for example, if you wanted the probability of x is equal to 0, that's just 0.26. That's how the table works. It just corresponds to each other. I'm just going to flip sides. They just correspond to each other. So the probability of x equals 0, like that, is equal to 0.26. And you can read off the rest of the probabilities as well. So probability of x is equal to 1 is 0.49. Probability that x is equal to 2 is equal to p. That's unknown right now. But since it's unknown, we're going to talk about how we actually can find it. So it's pretty self-explanatory. I should just write here, they're the probabilities. Pretty self-explanatory. But to find p, what we have to do is consider that all of the possible outcomes are in this table, and that's a really fair assumption because a probability distribution wouldn't be complete without all the possible outcomes. So for example, Liverpool doesn't have a probability of scoring more than 2 goals. They don't have a probability of scoring 3 goals, 4 goals, whatever, right? And I've done that on purpose because they haven't been playing that good, but in this case it makes it a lot easier to calculate because you only have 3 possible outcomes. So in this case, how do we find p? Pretty obvious. It's a probability condition, or I guess just a restriction on probability and numbers. It's the fact that probabilities and all the outcomes should add up to a probability of 1. So how I write that in this format is, let's just do sum of probability x is equal to x. That's just a long way of writing this, by the way. So probability of capital X is equal to lowercase x. I mean, you could just do the sum of probabilities is equal to 1, but I want to use the proper notation. So I just say sum of probabilities using that notation from this table is equal to 1. Okay, so what I get is 0.26 plus 0.49 plus p is equal to 1. Therefore, p is equal to 1 minus 0.26 minus 0.49. Let's do some quick maths. 1 minus 0.26 is 0.74. Minus 0.49 is equal to 0.25. Yeah, equal to 0.25. Cool. So this value here is equal to 0.25. I don't have to rewrite it in the table. I don't have to cross it out. Usually this table would be printed out and given to us if you're doing a test or an exam. So we could just leave it as p, but just note that p is equal to 0.25 for any further calculations. Now the second part of this question, determine the probability of x being equal to 2, given that x is greater than or equal to 1. So a conditional probability. In this case, what we do is just use the formula, intersect x is equal to 2 with x is greater than or equal to 1. And divide that by the probability that x is greater than or equal to 1. Now the intersection between x is equal to 2 and x is greater than or equal to 1, you can just see visually that it's x is equal to 2 because x is greater than or equal to 1 includes this value, and then x is equal to 2 is obviously just a subset of that. So this is just going to be equal to probability that x is equal to 2 divided by the probability that x is greater than or equal to 1. Now, x is equal to 2, we just found was 0.25 or p. X is greater than or equal to 1 is 0.74 because 0.49 plus 0.25. So therefore this value is 25 over 74. You can see what I've done here is just multiplied the top and the bottom by 100, and that's a really easy way of cancelling them out. And this can't be simplified any further because 25 only has multiple of 5. And it doesn't have, apart from 1 and 25, obviously. Sweet. We'll rub this out now, and we'll go on to a couple more examples, which is kind of an extension of discrete probability distributions. Now, for any different type of probability distribution, in the future we're going to learn different types such as continuous and normal distributions. They all have two characteristics that are really important for describing the distributions. The first one we're going to talk about is E of x, which stands for expected value. Okay, so E of x here, just going to write down, it stands for expected value of x. Expected value is just another way of saying the average or the mean as well, okay? Average or mean, okay? So what does that mean in terms of this context of the amount of goals scored in a match? So if I calculate E of x, it's just the expected number of goals or the average number of goals that we expect Liverpool to score pretty much. So how to calculate it for discrete probability distribution, and by the way, the process is different for different types of distributions. How we calculate it is we sum the multiplication of these pairs. So for example, I'm just going to write down the formula first. So that symbol for sum, and then x, which is the possible outcome multiplied with the corresponding probability. Okay, so that's the fancy way of writing it. This is the formula on the formula sheet, but how we actually interpret this from an algebraic standpoint is we multiply 0 with 0.26, and then we add 1 multiplied by 0.49, and when we plus 2 multiplied by 0.25. So I'm just going to write that all out. Plus 1 multiplied by 0.49, plus 2 multiplied by 0.25. So 0 multiplied by that, obviously just 0. 1 multiplied by 0.49 is 0.49, and then this is 0.5. So our final answer is 0.99 goals. Now, does it make sense that the number of goals that it's expected is not a whole number? Well, in this case, it is because it's a statistical average. So we wouldn't expect to round it or anything because expected value should be, you know, like it is never likely that a statistical average is going to be an exact whole number. Even in this case, if we're going to have whole number outcomes, because it is a probabilistic thing, it's fine to keep it as a decimal, and it's actually expected that we do keep it as a decimal. So on average, Liverpool is scoring just under 1 goal per game. And based on the probabilities, that kind of makes sense. And you can kind of see the numbers are very slightly skewed in the left direction because we have 0.26, 0.49, and 0.25 here. So the numbers are slightly skewed to the left. very slightly, and the left, I mean the left of 1, okay, the left of the middle value. So this kind of makes sense if you look at the probabilities. And yeah, again, as I mentioned in the previous part or the previous video, the numbers should always make sense when you look at the context. So in this case, this 0.99 does make perfect sense because the numbers are slightly skewed to the left-hand side of the table. Sweet. Okay. Now we're going to go ahead and calculate the variance. Hopefully the expected value or the average or mean value does make sense from a probability standpoint. The variance, I mean, you can kind of just imagine this word. I'll just use a different color actually to separate these working out. This is the variance. Variance, can't write. So the variance is a measure of the spread, okay? So a spread of a distribution. What the spread means is how far the possible outcomes, are literally separate from each other in the table or separated from each of the other values. So I'll show you two examples of maybe a high spread versus a low spread distribution. So for example, if I had to change these probabilities, right? Let's do two separate possibilities. So we have 0, 1, and 2. I'm not going to write out the full table, but 0, 1, and 2. Let's say we had 1/3, 1/3, 1/3. And then we verse that, 1, 2, 3, with 1/10, maybe not 1/10, we'll do 2/10, 4/10, 4/10. Okay, so we have two different distributions. We can see this one is equally distributed, and this one is not equally distributed. You can see the outside ones are much greater, pretty much double the middle value. Which one do you think has a higher spread? In this case, this one would have a higher spread because you have further numbers away from the middle. And you expect for each of these, by the way, the expected value, if you did calculate it, is the middle value exactly. I've done that on purpose because the variance is the spread from the expected value. So you can see in this case, you have higher probabilities away from the expected value. This one has lower probabilities in comparison to this one. So this one would have a higher variance, and this one would have a lower variance in comparison to each other. Okay, it's just an important thing to note. That's what the variance actually means from a statistical perspective. And if you did plot these, then the variance would just mean like how far away the graph is, like in terms of the peaks away from the expected value. But as long as you understand that it's a measure for spread, so this one is more spread, this one is less spread, then that's the most important thing that you need to know. So how do we calculate it? The formula for variance is e of x squared minus e of x squared on the outside. They're not the same thing. E of x squared is the same calculation that we did above, but we just square the outcome value. So for example, if we wanted to calculate e of x squared, I'll just do an arrow just to indicate that this is the e of x squared calculation. It'll be the same as before. It'll be 0 squared multiplied by 0.26 plus 1 squared multiplied by 0.49 plus 2 squared multiplied by 0.25. So 0 multiplied by 0.26, that obviously that's not even part of our calculation. 1 squared doesn't make a difference, so it's just 0.49 plus 2 squared, which is 4 multiplied by 0.25. So that's the part of the calculation that slightly changes. 4 multiplied by 0.25 is 1, so this value would be 1.49. And by the way, this was the calculation for e of x squared. Again, it's just the outcome squared multiplied with the probabilities, and then we'll add it together. Now, e of x squared is equal to 0.99, or the expected value just squared on the outside. 99 times 99, I actually don't know what that is. Let me do a quick calculation. Okay, I've got the trusty app calculator on my laptop. We've got 0.9801. I'm just going to make it 0.98 just to make it easier to calculate things. So therefore, the variance is equal to 1.49 minus 0.98, which is equal to 0.51. Yeah, cool. Cool, the variance is equal to 0.51. Now, in terms of like how we interpret the number, it's not as easy to interpret as the expected value. The expected value is clearly a finite thing that we can compare with our statistical values. The variance is a bit harder to compare because there's not a kind of a set way of, saying, okay, is this number correct? Does this spread of 0.5 make sense? It can't really interpret it from that from that statistical standpoint, comparing it with our discrete values. So we kind of just say, okay, the variance, we probably did the calculation right if you use the formulas right, so it's going to be equal to 0.51. Now, a key thing to note with variance is that you might recognize spread, the term spread, kind of being associated with a term called the standard deviation, especially if you've done further or any sort of statistics content in the past. So variance is actually related to standard deviation. Standard deviation is that. So if I have standard deviation of that, it's equal to the square root of variance. Okay, so this is standard deviation. And this is obviously the variance. So that's how they're related. The standard deviation is just the square root of the variance. So the question asks you to calculate the standard deviation, you just square root this variance value and you would get the standard deviation. Now there's a couple of useful properties of standard deviation, but they don't really apply to a discrete case. And the reason for that is because a discrete case, you can see here, we've only got 3 possible outcomes. And the properties of standard deviation, such as, I mean, you might have heard of the 68, 95, 99.7 rule. If you don't know it, it's fine. It's going to be taught in a later topic in methods. But if you're kind of curious, oh, does that apply in this case? Well, not really. It should apply, like, theoretically, but because we only have 3 outcomes, we don't have a big sample space. So you can't really see those properties being exhibited. But if you did have a wider sample space and you did have more values that were maybe normally distributed, you would more so see the properties of standard deviation being applied.